Okay, in this lecture we're going to continue on in Chapter 8, starting at 8.151, and finish out Chapter 8 in this lecture. So we've been talking about subnetting, and we're kind of talking about the waste again. We've talked about how subnetting in general, in Class A, Class B, Class C, networking is wasteful. So they're just going to talk about what they're calling basic subnets, which is referring to equal size subnets that we've been talking about, and talk about the waste once again. So here on the screen, we have a topology that has 4 routers that are connected together, and each of those routers is in a different building and has a different number of hosts. So mention this because it's important. If we talk about broadcast domains, again, a lot of students would be tempted to say there are 4 broadcast domains in this topology, but there's actually 7 because we have to worry about these wide area network connections between them. So if we were going to do this the normal way that we've been talking about subnetting, we would say that we need 7 subnets, and we would solve for 2 to the n is greater than or equal to the number of subnets we need, and the value of n, smallest value of n that makes that true, is 3. So we see a basic subnet scheme like we've seen before. We borrow 3 bits out of what was the host portion, and then that gives us 5 bits now in the host portion, and we have 8 subnets when we do that because 2 to the third is 8. We're only going to use 7 of those. And then as far as the host portion, the usable number of hosts is 2 to the number of bits we have, which is 5, which is 32, minus 2, one of those for the network address and one for the broadcast address, which gives us 30 usable hosts per network. And if we go back to figure 1 real quick, we'll see that this comes close. We need 28 hosts here, but 30 will accommodate us as far as number of hosts or number of IP addresses that we have. So if we move on to figure 3, they're talking about they're talking about subnets 4, 5, and 6, which are going to be the wide area network connections. So we have 30 usable host address. We only have 2 IP addresses in between those routers, 1 on each interface. So there we're wasting 28 addresses. Now, the one thing I do want to point out is if we have 30 IP addresses, we're wasting 5 here, we're wasting 10 here, we're wasting 15 here, we're wasting 2 here. Not as bad as the 28 that we're wasting for those interconnects, but it's still waste nonetheless. So to fix that problem, we have something called variable length subnet mask. So what we've seen up to this point when we create fixed size subnets is, if we have a /24 and we borrow 3 bits, then every subnet has a /27 subnet mask. So with variable length subnet mask, we're going to change that. So here they're showing that we have equal size subnets. In this case 8 that are size 30 using the previous example. But what they're going to show us is that we can take a subnet and subdivide it even further. So basically variable length subnet mask implies that you're going to borrow more bits, i.e. you're going to subnet the subnets that you've already created. So how are we going to do this? So in this example, they're showing that we're going to take the last subnet and we're going to subnet it even further so that we have WAN connections. So what we're going to do is we are going to borrow 3 more bits from the last subnet, so that's going to become a /30. Actually, it's going to become a whole lot of /30s. I don't know if you recalled earlier in a previous lecture, I mentioned that we had to have at least 2 bits in the network portion and at least 2 bits in the host portion for it to be a valid subnet mask. And here's the perfect example of why. If we have 2 bits in the host portion, which is what we're ending up with at the bottom of this figure, 2 to the 2 is 4, minus 2 is 2, so we only have 2 usable IP addresses, and that would be for the 2 hosts that are in that wide area connection. If we went to tried to do a /31, then we end up with 0 usable host. So that doesn't make sense. So this is just a good example on the screen to discuss that. So this video discussion is talking about the same thing, but it's only 2 minutes and 32 seconds long, so I think I am going to play this to give you an alternate presentation and possibly some more information.
The basics of VLSM, or variable length subnet masks, works like this. 1. Subnets do not have to be equal sizes, as long as their address ranges do not overlap. So we can create unequal sized subnets. They do not all have to be the same size. 2. When creating subnets, it is easier to work from larger to smaller subnets. So for example, I have the 192.168.1.0/24 network. I subnet the network into 4 subnets /26 subnet masks, so the subnets go up by 64. I now have 4 equal-sized subnets. With VLSM, or variable length subnet masks, I can decide that I want to change one of these subnets and further subdivide them into smaller subnets, as long as the address spaces that I create, or the subnets that I create, do not intrude into the other subnets. For instance, I could take this 192.168.1.192 subnet. The address range for this subnet goes from 192 all the way up to 255. What I can do is I can say, instead of having this subnet /26, what if I take that address space and divide it into 2 smaller subnets size /27 each? If I do this, I effectively have created 5 subnets. The 3 subnets up here are 64 hosts each, and the 2 new subnets that I created from the 4th subnet are 32 hosts each. The reason I can do this is because my 2 smaller subnets do not intrude into the larger subnets. This is variable length subnet masks. In this situation, it has also allowed me to create 5 subnets, thus escaping the equal-sized subnet limitation of creating subnets in powers of 2. This gives me greater flexibility and allows me to create subnets of different sizes based on the requirements of my network.
Okay, continuing on, this page 8155, which has 5 figures on it, is talking about VLSM, variable length subnet mask, in practice. So here we are seeing something similar to what we had before. We had 4 buildings. Each building has a LAN that's connected to a router, and each of those 4 routers are connected by a wide area wide area network connection that needs 2 IP addresses. So they've already taken a /27, assigned it to building A, B, C, and D, and then further subnetted that down, the last subnet, to a /30, so that we have 2 IP addresses that can be used on both ends of these wide area connections. So that they've already done the VLSM math similar to what we've seen previously. Now then, some things they talk about here is they're going to use the first IP address to be the router interface. So in building A, the default gateway is going to be 192.168.20.1. In this network, this is the network address .32. .33 is going to be the IP address for the interface on this router. The 64 network, we're going to use .65, again, the first usable host IP for the router interface. And then likewise over here in the .96 network, we're going to use .97. Again, that is not required, but that is a very, very common thing to do. So now what we're going to do is we're going to go through and look at some of the iOS commands. So what they're going to do on each of these routers, in this figure, router 1, is they're going to go in, they're going to get into global configuration mode, they're going to pick an interface, they're going to give it an IP address, and then the first set of commands is doing it for gigabit 00, which would be here. And then the second set of commands is doing it for serial 0/0/0, which is going to be this wide area connection. If we go to the next figure, they're going to do the same thing for router 2. Notice they have to do 3 IP addresses. So first they do the gig interface, then they do the serial address, and then the other serial address. Likewise, on building C, we're going to have 3 different interfaces that we have to set IP addresses on. And then finally, on router 4, we have the gig interface that services building D. And then we have the wide area connection that's going back over to router 3. The other thing you should be familiar with is in this topology diagram, they've used the slash notation to represent the network mask, but on the iOS commands, those need to be done in decimal dotted notation. And you've had some homeworks where you've had to do that yourself, but I just wanted to point out that you do have to make that change or that calculation before you go into the router, into iOS, and do that. This is showing you the basic subnetting of that original .20.0 network that was a /24. So these are telling you the host you have, and then here they're just pointing out that you can go through and take a subnet and divide it even further to get those WAN addresses. Now then, the one thing I don't really like about this is perfectly fine, but because of the way we're going to look at variable length subnet mask, when you don't have LANs that are the same size, is we would have actually used this .128, the first unused, and start subdividing it instead of jumping down to the last. What they've shown here is fine, but I have reasons that I'm telling you that you really should use the first unused one if you're going through and doing this yourself. This video demonstration is going through and talking about VLSM. It is about 10.5 minutes long, so I think you should probably watch that on your own. Here's an activity that is kind of telling you, what's the new subnet mask, what's the first full subnet, what's the last subnet, and you have values over here that you can draw in. So you can do this on your own. Also notice that figure 1 has a problem, and then figure 2 has a different problem, so that you can practice and not be looking at the exact same activity over and over again. 8.2, specifically 8211, is talking about planning IP assignment, anytime you're planning a new network, the first thing you need to do is you need to sit down and decide how you are going to associate local area networks with each other. We've talked about that before. In this case, the assumption looks like we're at a school, and we're going to have a subnet that student devices are on. We're going to have a subnet that faculty devices are on, and then the school administrators are going to be on their own network. So another thing we have to decide is, are we going to use public or private IP addresses? They're pointing out over here in the text that we have a Class A, Class B, and a Class C private address, sometimes referred to as non-routable. So a lot of times you will use private addresses instead of public for everything. There's some security reasons to do that. UK is moving more and more to that. KCTCS, when they set up their network, everything is on, as far as I know, a 10 dot something private address that is private within KCTCS. Now then, once you've decided how you're going to divvy up your devices, then you need to start giving out IP addresses or coming up with a scheme to give out IP addresses. And there are three primary considerations that are shown here. You want to make sure that you don't get duplicate addresses. If you have two hosts that have the same IP address, they are not either one going to be able to communicate with the network correctly. And if you do something like accidentally give a host the default gateway address, in addition to the default gateway having that address, that's going to cause real problems on your network. The other thing that you want to do is you want to provide and control access. So, you might not want servers to be able to get to from the outside your domain, outside your company. Sometimes to do that and deal easier with the control access is you'll come up with a scheme. First valid IP address in the subnet is the default gateway, the interface on the router that services that LAN. Then you might say 250 through 254 is reserved for networking equipment, and maybe 240 to 249 are reserved for servers, and 235 to 239 is reserved for printers. So that way you can better know what a device is just by looking at its IP address, and possibly set up access control list to control access to those various things I just mentioned. And then you always want to monitor security and performance to make sure your network is secure and make sure it's performing correctly. And again, by using private IP addresses internally, that gives you increased security on that network. This is a similar scenario, very, very close, I think, to what I said, except I flipped printers and servers maybe, and only maybe allowed 5 printers instead of 10. But the point is, here's another example of how you might go about setting up your devices. And again, I said that the first usable host device is going to be our default gateway. I've said this a zillion times, but that's a very common thing to do. Okay, 8214 is a packet tracer talking about VLSM. It's not terribly long. It's 4 pages long, but the 4th page is suggested rubrics, so it's only really 3 pages long. I will assign this, so watch for it to appear in Blackboard. 8215 is a lab talking about the same type of thing. Since this has a kind of more complex topology that you have to deal with, it's 3 interconnected routers with subnets that have thousands of hosts on them. I'm going to hold off assigning this for the time being. If we can do this in the NetLab, I will do this one or assign this one later in the semester to be done on the NetLab. Okay, 8.3, the IP6 global unicast address is what we're talking about. So we talk a lot about subnetting in IP version 4, but since there's so many IP addresses and so much address space with IP version 6, it doesn't really need to be subnetted to conserve address. Basically what they're showing here is they call this hierarchical logical design. It kind of is subnetting, but we don't vary from this, is why they don't really call it subnetting. So what happens is the first 48 bits is something called a global routing prefix. So this is how we route between ISPs and regional internet registries. The next 16 bits is what they are calling the subnet ID, and this is used by an organization to have up to 2 to the 16 minus 1 IP addresses. So a lot of addresses, or I'm sorry, a lot of subnets. And then within that subnet, you have 64 bits. So you can actually have 2 to the 64 minus 2 host addresses. So lots and lots of hosts and lots of subnets with the way they've set up IP version 6. The subnet ID allows for 65,536 subnets, and it would be 0 through 65,535, the minus 1, because almost always in computing and networking we start at 0, which is why you have that negative 1. So what they're showing you here is that you, in this octet, can go from, these are hex digits, so you can go from 16 zeros through 16 ones. So those are going to be our 65,536 subnet IDs within any address block that we're given in IP version 4. This is basically the same as borrowing bits. You can actually do this. The main reason you would want to maybe restrict these or use different subnets would be for good design and security of your network. If you do borrow bits out of your host bits, it's best to do that on the nibble boundary. I don't know if we talked about nibbles, but these days, if you're asked what a byte is, the correct answer is 8 bits. A nibble is 4 bits, so half a byte is a nibble. It's kind of corny, but don't know who came up with that. And the reason you like to do it on the nibble boundary is because that 4 bits relates to 1 hexadecimal digit. So if you do subnet, you want to do it borrowing in groups of 4, basically. Okay, so here we have a topology. If we ask how many broadcast domains there are, there's 1, 2, 3, 4, 5. Don't forget the wide area network. So what we want to do is we want to go through and give IP version 6 addresses to this. Now they've used .1 for the router interfaces, and they're using .10 in this case for one of the PCs that is in each of the local area networks. So what they're going to do is we need 5 subnets. So they're just going to take the first 5 subnets, 0, 1, 2, 3, 4, 5, and use those. This is how they're going to do this. So it just looks a little longer because it's IP version 6 instead of IP version 4. You know, normally you would think about there being a cloud here, and this would be the network number of the cloud. There'd be a cloud here, etc. And then here in the last figure, for router 1, they're showing you how you go in and configure IP version 6. I think we've seen this before, but instead of saying IP for the command, we say IPv6. And in the case of IP address, we had to give an IP address, space, subnet mask. In the case of IP version 6, we're going to still need the keyword address, and we're going to give the address, and then we're going to put slash, and then use the slash notation for the subnet mask. So, you know, same ideal, just slightly different when we're dealing with IP version 6. This is a packet tracer exercise to go through and subnet for IP version 6. I will look over this and decide, so this may or may not appear in Blackboard. I will just look at it and decide if I think it is worthwhile to do. And if so, I will assign it. Okay, I believe activity 8011 was can you call me? This is class activity. It's like, okay, we've gone through chapter 8. We've talked about subnetting. Can you call me now? I am not going to assign this. It's basically doing the same thing or thinking about the same things you thought of as the class activity at the beginning of chapter 8. However, using your knowledge of variable length subnetting and subnetting in general to answer it. So I will not assign that. 8412 is a skills integration challenge. I may or may not assign this. I'll look over it and see how useful I think this would be, and if I decide it's useful, then I will assign it in Blackboard. And that brings us to the Chapter 8 summary. You know, I never read the summaries to you. It's just recapping the highlights of what we talked about in the chapter. So you might look over those to make sure they all sound familiar and you're comfortable with them. And with this being the end of Chapter 8, you should watch for an announcement that your Chapter 8 exam has been activated in the Cisco Networking Academy site, netacad.com. And I will probably have another supplemental lecture that talks about network math some more. Some of it may be review, but there will at least be some examples on variable length subnetting, which is, you know, what we talked about in this lecture.